Well, let's begin our journey into the complex plane. Did a little review in the last one. I think now we're going to get into it. And this isn't so bad. I'm just telling you. It's not that bad. We get over this little hurdle. We're going to be off and running. Okay. We're going to talk about like graphing these things. It's like, graphing. But it's not that bad. Okay, so let's look at our first one here on the left. And I ask you to go graph this. And if you start doing one of these, it's not going to work. I ask you where, on the XY axes, where are you going to put an imaginary or complex number? There's an imaginary part to this. It does not go there. That's why I've written this in red. We can't graph it on the XY graph. There isn't a spot for real or for imaginary numbers. There's spots for real numbers. So we have to trash this whole thing, but we're going to stick with something that we're relatively familiar with. So instead of calling it the x-axis, we're going to call this the real axis, or the real portion, like this, like that part. That's going to be like our x values, but they're not x values. We're just saying it's the real portion. We come up here and we're say what we traditionally think of as our y-axis, and we're going to say nope, that's now the imaginary axis. So we're going to take whatever number is attached to the I, and that's going to be like our y value. So let's graph it. And we're like, okay, so our real portion, we're going to go -2. So we go to -2, where we typically graph x being -2, but now we're going to say that's just our real portion. And now we're going to look through and say, all right, and now on our imaginary portion, we have that +3. So we're like, well, let's go up 1, 2, and 3. There it is. So it's like just graphing x comma y. And there it is. We got our z. Yeah, buddy. We have now graphed in the complex plane. Well, we'll mess around with that one in just a second. Let's come up with a new one. Let's call this one, I'm going to call it W this time. Just mixing it up on you. Let's go with -3i. That's a complex number. That is definitely a complex number. So where are we going to graph this thing? Well, wait. Now this is the real number portion. This is the imaginary, or axes. Well, it looks like we have no real number part, right? There's a 0 there. So, I mean, we won't want to put it at 1 or 2 or -1 or -2. I think it's got to be right there on the imaginary axis. And then we're going to look down and go, well, 1, 2, and -3 in the imaginary, -3. We're like, well, that's where it's going to go. So it's actually just going to sit right on the imaginary axis, because our real is not -2 or -1 or 1 or 2. It's 0, which means we must be right there on that imaginary axis. And there we have it. We've now graphed it. So it's saying we have no real portion. We only have an imaginary portion, and we're there. This isn't so bad. It's like doing an ordered pair. Could you do this? Like aside, this isn't right. We're saying -2, 3, and this one being 0, -3. You know what I mean? This is how it gets graphed. We get accustomed to it. And we're going to go kick some butt when you do it for the 1,000th time throughout your homework. Well, we're gonna have another piece to this. Something we're gonna want to ask ourselves. We're gonna want to know, how far away is it from the frickin' origin? You know, it's from 0, 0 to these points live. I mean, we want to know how far, and we have a name. I think your book calls it something a little different. They call it just the absolute value of a complex. It can also be called like the modulus, the magnitude. Okay, so some other synonyms of this. I'll probably throw most of them in there. But if we want to know Now, this absolute value of a complex number represents the distance back to the origin. So if I was to ask you, do you think you could figure out how long this line is? After doing trigonometry for how long? Just make a frickin' triangle. You know what I mean? A squared plus b squared equals frickin' c squared. So, if we say that our z is written as a plus bi, remember that? That's from the first one. So we're saying, like, for our example up here, our a is -2 and our b is +3. So we want to find the absolute value of that complex number. We write it. Absolute value would be absolute value. And it's just going to be the square root of a squared plus b squared. Because this length could be c on a triangle, and a squared plus b squared equals c squared. So let's solve ours out in blue. So we're going to say that the absolute value of our -2 plus 3i is going to be equal to the square root of, and we square it up. Don't bring the I, just the numbers, the -2 and the 3. So that's going to be what? 4 plus 9, that's root 13. And we find out that our length, our absolute value, our modulus, our magnitude, is going to be root 13. Now, I'm pretty sure we don't really need to get too crazy to find out how far it is. What's the difference between -3 and 0? Because the absolute value is always going to be positive, just like the hypotenuse is always positive, right? And we're like, how far away is it from 0 to -3? 3! It's freaking 3, right? It's not 7. And just to show it, we say, all right, we'll take the absolute value of this sucker. So this is going to be the square root of 0 squared plus, just bring the 3, don't bring the I. And you get the square root of 9, which is equal to, holy crap, who would have ever saw that coming? It's equal to 3. So this is how we're going to plot, and this is how we're going to find the distances between the two. Okay. Let's look at some. Let's look at 2 new ones. Let's look at 2 new ones. And what we're going to do in the end is we want to find what's z plus w. And if you did any vector homework, you might be good. Oh, you know what? I need to change something. Real quick. There we go. -3 minus I. I didn't make my scale big enough for this. All right, so let's plot them both individually. So let's plot z. So it's going to be 4, 2i. So there's z. And then w would be -3 minus I. So that'd be like a -1. And then here would be your w. Neato, huh? Now, let's draw lines out. Like, remember, like with vectors? Go like this. And got this one's going to go like that. Cool. Okay. So I just wrote them individually. Let's add these things up. Let's do z plus w. Let's figure out what we get from that. This is going to be equal to, so 4 plus -3 is equal to 1. And 2 i's minus an I is going to be equal to just one of those i's. So there's z plus w. We get 1 plus I. But wait, let's get rid of the w real quick. So let's say our first direction is, I want you to go 4 units over to the right, and then I want you to go 2 units up. Now it's saying we want to add new directions. We're going to go to this one. It says, all right, now I don't want you to be, no. I don't want you to be at 4 anymore. I want you to go back by -3. So we're like, all right. Or don't go back by now. Go -3. So we're like, well, let's go back one. So we're going to go 1, 2, 3. All right. So we go back by that. And then it says we're supposed to then go back down by 1. So we're going to go back down by 1. So where's that end up being? Oh, isn't that going to be 1, 1? Because we're going down from 2 which will get you to 1. And we go back from 4 3 units, which will take you to 1, which would be right here at a 1 plus I. So this would just be the addition of vectors. Oh, shoot, did I say vectors? I mean complex numbers. It's the same frickin' thing, except we have it on a different sort of axis. Now, I know I'm not showing this wonderfully, but I think the point's kind of getting across. If you looked at your vectors, we're kind of just doing the same thing. And then when we get to our polar, you're going to notice we're doing the same freaking thing. All right. Well, I think I'm going to stop at this point. I think you have enough to do most of your homework. Maybe I'll come up with something kind of tricky for another one, but I'll see you soon.